Welcome to Calculus. Today we will investigate how to find volume with cross sections, and we're specifically going to consider cross sections that are either a square or a rectangle. We'll take a look at two examples. Our first example is given in words and also a graph of my base. So we're told here that the base of a solid is the region enclosed by a circle with a radius of 6. So I can see my circle base there on the coordinate plane. I'm going to try to find cross sections that are perpendicular to the x-axis and they are squares. So just to kind of visualize the solid that we're going to try to calculate volume for, it's this circular base. And then what I'll have are square cross sections that are perpendicular to the x-axis. So just to pick up some examples of these square cross sections, they would be represented by this base that's defined by the circular region. So I'm just kind of randomly selecting a few of these bases. And then just to kind of visualize, these are squares that would be projected up into the third dimension. So definitely it's a solid. Really, that looks a lot like a canister or a cylinder. So that's kind of a visual attempt to say this is a three-dimensional object. And in fact, it's going to be something like a cylinder. So we want to actually calculate the volume of that. So I'm going to get rid of these drawings. And what I want to do is just kind of set up the integration just conceptually first. So basically, we're going to look for the volume to be given by the integration from my extreme left on the x-axis, and that I can pick because these squares are perpendicular to the x-axis. So it's going to be from A to B. For us, that's going to be from this extreme left, -6, to the extreme right, +6. And then in terms of the integration, what I want to do is kind of think, okay, how would I calculate the area of a square slice? Those were those slices that we drew. So it's basically going to be the base times itself, because remember the area of a square is base squared since all the sides are the same length. So this is going to be the base defined by a circle. So this is very approximate. We're not even using functions there. I'm just saying what it should be. And then I'm squaring that. That's one of those slices. And so then conceptually, what I'm trying to do with the integration is add up the area of all these square slices. They're going to change in their dimensions according to where they fall along that circle. So in fact, it's not going to be a nice can like a canister. It's going to have a curved top to it, since the squares will decrease in height as the base decreases along the circle's kind of cross sections there. Okay, so that's conceptually what we're going to do with this. So what I need to do is figure out how can I represent the base defined by the circle. So really that has to do with finding the area of this circle, and we're going to define it in terms of x. So they'll look like functions. So I just need to pick up the equation for a circle. So just from geometry, we're going to say that our circle is going to be defined as x minus x1 squared plus y minus y1 squared equals r squared. So remember, a circle is defined in a way like our Pythagorean theorem. And this comes from two things. So my center is going to be defined as x1, y1. And then just thinking back to how Euclid defined a circle, it's really center and radius. And radius is going to be given by r. So I happen to know these values. The center here is the origin. So x1, y1 is 0. So in terms of setting up our equation, it's going to be x minus 0 squared. So it's just going to be x squared plus y minus 0 squared, which is just y squared. And then we know that our radius is 6. It's given there in the words, and also I can see it on the graph. So for our equation, that's going to be equals to 6 squared. So since my square cross sections are perpendicular to the x-axis, I want to solve for y. I want to make this a function. So what I'll do is I'm going to subtract x squared. And that'll give me y squared equals 36 minus x squared. And then to finalize solution for y, I'm going to take square root of both sides, and that's going to give me this really double set of functions. Y equals plus or minus square root 36 minus x squared. So just to identify which is which, my positive version of this circle, so I'll just outline that positive side, is going to be given by y equals positive square root 36 minus x squared. The negative version is going to be given by this, well, it'll represent this lower part of the circle. And that's going to be my y equals negative square root 36 minus x squared. So that gives me a way of actually filling something in here for base defined by the circle. So let's start with our integration. So for us, our volume of this solid is going to be equal to the integration from -6 on the far left to 6 on the far right. And then I want to subtract, since I'm finding the area of that base, the upper minus the lower. So square root of 36 minus x squared minus negative square root 36 minus x squared. And then because these are square cross sections, I'm just going to square that for the area of the base and then add them all up to find volume. So dx is going to be representative of the width taken down to 0. So that's our setup. And at this point, we can start integrating. So I'm going to start here in the integrand here. So I notice that minus negative is going to become plus, and those two red and green radicals are the same. So it's basically 2 of them. And then I'm going to square it. So that's going to be equivalent to the integral from -6 to 6 of 4 times 36 minus x squared dx. And at that point, I can let the 4 really kind of do one of 2 things. I can either let it totally leave the integration, or I can distribute it through. So I'll let it leave. And then I want to integrate here. So it's going to be times 36x minus 1/3 x cubed. And again, I'm going to integrate from -6 to 6. So at that point, I'm ready to actually complete the integration by applying fundamental theorem of calculus. So this is going to be equal now to 4 times 36 times positive 6 minus 1/3 times 6 cubed. Put all that in parentheses minus 36 times -6 minus 1/3 times -6 cubed. And that gives me my setup there for calculating this area numerically. So I just want to start simplifying here. This is going to become 4 times 36 times 6 is 216 minus 1/3 times 6 cubed is going to be minus 72. And then picking up with my second expression there, it's going to be minus, and then again, I got -216 plus 72. And we'll keep going here with our simplification. So this is going to be equivalent to 4 times 144 from that first one. And then distributing the negative through, it's going to also be plus 144, which is going to be equivalent to 4 times 228, or 1,152. And again, that's a volume. So if I were to include units, I don't really have units here, it would be cubic units. So that's for an example of a circular base where my cross sections are squares that are perpendicular to the x-axis. Let's take a look at an example where we have an ellipse as the base, cross sections perpendicular to the y-axis, and rectangles instead of squares. So here I don't have a graph, but I can see that my solid has a base that's defined as an ellipse. So I'm going to just identify it here. It's x squared over 25 plus y squared over 36 equals 1. So just to get a sense about what we're really trying to calculate volume for, I'm just going to sketch a graph of that elliptical base. So there's x and y. So I see that I've got both a major axis and a minor axis, and I've also got center at kind of the same definition as our circle. So remember, for an ellipse, the center is given by x1, y1, x minus x1 squared over, here we'll just say that this is 5 squared for us, plus y minus y1 squared over 6 squared equals 1. So my center is given by x1, y1. Since I have nothing in terms of numbers with my x squared, y squared, my center is the origin. And I've got the minor axis here is given on the x dimension. I know it's a minor axis because 5 is smaller than 6. So I'm going to go out 5 in each direction. 1, 2, 3, 4, 5 to the left. 1, 2, 3, 4, 5 to the right. And then my major axis is in the y dimension, it's 6. So 6 in the positive and 6 in the negative. And there's my ellipse. So my elliptical base, and this is a little bit exaggerated just so we can see it's an ellipse and not a circle. That's my base. So again, that's kind of how we're defining this base. And what I want to do at that point is then think, okay, how are my slices going to be arranged? So I see that definitely for this example, my slices are now perpendicular to the y-axis. So if I just pick a few of these, just randomly select a few slices, these are the pieces that are going to make up my volume, and they're not squares, but rectangles whose height is half the length of the base. So it's not going to be as tall, and I can't just square it to find their area. So that's kind of the idea there. So just to distinguish from our first example, here our base is an ellipse instead of a circle. It's defined in terms of y instead of x. And also my slices are rectangles, not squares. So there's at least 3 differences here from our first example. So again, I want to set up the integration conceptually first. So it's integration from the lower part of the graph. So that's going to be given as -6 again. To the upper part of the graph, 6. And then let's just write this in words just now. So this is going to be the area of rectangles. In fact, let's define that a little differently, since it's going to Well, you know what? We should probably just write that. So it's the area of rectangles defined by an ellipse. So I'm not going to put a square here. We'll end up trying to square it, but we have to do a little algebraic manipulation, and then dy, because my slices are perpendicular to the y-axis. So what I'd like to do is I'm going to start off by defining my function first. And really it's a relation because we're in the y dimension here. So I'm going to take this elliptical equation and I want to solve it for x. So let's just start there. So it's going to be x squared over 25 plus y squared over 36 equals 1. So I'm going to solve for x here. So it's going to be x squared equals 25 times 1 minus y squared over 36. And then to get rid of the square again, I'm going to apply the square root both sides. And so we get this equation. And again, it's going to be for the right side and the left side. So x equals the plus or minus the square root of distributing that 25 through 25 minus 25 over 36 y squared. And so what I'll identify is my left and right side. So my left side is going to be x equals negative square root 25 minus 2536 y squared. And my right side, same expression there, but positive. Y equals positive square root 25 minus 2536 y squared. And I'm so used to dealing with functions, I put y equals when it should be x equals, but that's a quick fix. So that gives me my right minus my left. So we're going to use that setup there. What I need to do though is figure out how to deal with the fact that these are rectangles instead of squares. And so what I'm seeing is that this is like, if I think about these rectangles, so let me just bring one kind of out of this arrangement. So if I've got a rectangle, so I'm just going to kind of consider it here like in a thought bubble. We're going to define this base in terms of the right minus the left of that ellipse. So I can just call it, I don't know, x. The half or the height here is y, but what I know is that y there is half the length of the base. So instead of using y, I'm going to call it half x. And that is how I'm going to treat the area of rectangles defined by the ellipse. So we'll start to set this up. This is going to be equivalent. So volume equals the integration from -6 on the lower side to 6 on the upper side of basically half x squared. So if I kind of use that arrangement for the area, I can just pull the half out of the integration and then treat this like squares. And you can kind of think, okay, the area of a rectangle whose height is half its base is going to be half the area of the square with the same base. So that kind of geometrically all fits together. So we're going to go with it. And then it's right minus left. And again, we got to do that because these rectangles are perpendicular to the y-axis. So the right side was the square root of 25 minus 25 over 36 y squared minus negative. So we're seeing that kind of duplication of the relation here, just like with the circle in our first example. And I forgot my square there on the y. And then we'll pick up, close the integrand there and write dy for the slices. So we've got it set up. And at that point, what I want to do is then just simplify, integrate, and then evaluate using fundamental theorem of calculus. So now my integration is going to be half integration from -6 to 6. I forgot something here. Should have a square there. So what that'll do is I've got this radical plus the same radical. So it's two of them, square it. So that's 4, which I'm going to pull outside the integration. And then on the inside, I'll have, without the radical, 25 minus 25 over 36y squared dy. So that's at this point ready to integrate. So I'm going to write down here, this is now equal to 2 times. So I'm going to integrate this integrand 25y plus -25 over 36 as a factor or coefficient there times 1/3 y cubed integrated from -6 to 6. And at that point, I can plug numbers in now to evaluate using the fundamental theorem of calculus. So that's going to be equal to 2. So I'll plug in +6 first, so 25 times 6. If I combine those fractions, that's going to be -25 over 108, 6 cubed. And then subtract from that the same expression, but now with -6 substituted in for y. So 25 times -6 minus 25 over 108 times -6 cubed. And close my parentheses. So now I just have to simplify that expression. So I'm going to note here that this is equal to 2 times, so 25 times 6 is 150. And then 25 over 108 times 6 cubed, that really reduces down conveniently to 50. And then I've got same values here, just opposite signs. So -150. And then a negative times the negative from the cube is going to be +50. So that's reduced down quite a bit. That's going to now be equal to 2 times 150 minus 50 plus 150 minus 50. So just picking up that parentheses group, it's 150 minus 50 is 100. So there's 2 of those groups. So it's 200 times 2. The volume here is really cleanly 400 cubic units. Thanks for joining for these 2 examples. So one that was a circular base with square slices that were perpendicular to the x-axis. And then the second example, a solid formed by an elliptical base where the slices were rectangles perpendicular to the y-axis. See you soon.